Thanks, Simena, for the introduction. So I'm talking about sketching methods for efficient correlated dataset search. And this is joint work with folks at the Visualization, Image, and Data Analysis Lab at New York University. So let's get started. Today we are seeing an immense increase in our ability of collecting and storing data, right? And this, together with this trend towards openness and data sharing among organizations, is leading to increasing availability of structured data, right? And this opens up opportunities to enrich data analytics and to improve machine learning models. Now we have the opportunity to combine data sets from different sources and make them richer and improve our analysis, right? However, this data abundance also makes it harder to find data sets. In this context, we are seeing lots of data set search and discovery solutions. They are emerging as a critical capability in the organizations. Now we're seeing many startups and product offerings from many companies that are starting to tackle this problem of data set search and discovery. And in this talk, I'm gonna essentially talk about this topic, and I'll start first with an example to illustrate the problem we are working on. So suppose a data scientist from the New York City Taxi and Limousine Commission is tasked with building a model to predict taxi demand in New York, right? She has this initial data set, which contains a few columns such as pickup date time, location ID, and her goal is to predict the number of trips at a given time and location. So she trained a random forest regressor, and she obtains this mean absolute error of 66, which is not great for this data set. So at this point, the question is, how can we improve this model? How can we find additional useful features to improve this model, right? And by discussing with experts, they come up with a solution. An expert suggests that, well, why can't you include new features such as weather indicators? Perhaps if it's raining, then people are more willing to take taxi trips, right? So what she does is she goes to the web, she tries to find new data sets, she types NYC weather, and she finds several data sets related to this. Now the problem is, now she has several data sets. She needs to download each of them manually, and then she needs to try to combine these data sets one by one with her original data set. Eventually, she finds one which contains features such as temperature, average temperature, and precipitation. She combines this with the original data. And then using the augmented table, she retrains the model, which improves the results. And she gets a 41% improvement over the original result. Now, there are many other data sets. For example, she could have searched for city bikes, the number of bikes in the streets, if the day is nice, or people will be more willing to bike or something like that, right? But there are many data sets. So for example, in the New York City Open Data catalog, there are thousands of data sets about this. In the previous example, 34 data sets. So, and of course, in the web, there are many more that could improve. So the question is, there are just too many data sets, and how can we decide which ones will improve the model? Which ones are relevant to our task at hand, right? And another problem is this is all hypothesis driven. So the experts, they need to use their intuition and their prior knowledge to search for the new data sets. They first need to come up, maybe weather will improve. So one of the key things we are looking at here in our research is how can we improve this process, right? So if you take a closer look at the problem, essentially we have a number of data sets, lots of data sets in a data lake or in a data repository. And then we have our query table. In our example, it was the taxi trips. The first task we need to do is to find which data sets are joinable. once we know which ones are joinable, we need to materialize the join and add a new table to the dataset. And only then we can train a new machine learning model, and then we can evaluate and compare performance between the new model and the previous model. Of course, this is too expensive. It's infeasible to do at large scale for many datasets, right? And this is actually the core question in our research. How can we efficiently find variables which help predict a target variable in large-scale dataset collections? So, yeah, in our research, we essentially propose a new data-driven approach for this problem. And yeah, so one intuitively, right? What are good features? Typically, good features, they are correlated with the target variable that you want to predict. And this intuition has been used in many feature selection algorithms, for example, in the literature. And inspired by this idea, we are exploring this new approach, which we call joint correlation queries, which essentially, it's a query that takes as input the data set, the data set that we are working on, and it outputs tables that are not only joinable with this data set, but also that have other columns that are correlated with our target variable in the query data set. And why do we care about correlated data? One of the reasons is I just mentioned one of the reasons, right? Feature selection algorithms usually take this into account, but there are also many other applications that could benefit of finding correlated data. For example, for understanding real-world phenomena and confirming or refuting hypotheses. So for example, one of the most well-used techniques in data analysis is actually doing linear regression to predict or to explain some features of interest. In our case, for example, we could fit a linear model in our data. In our case, the y variable would be the number of taxi flips, and we could be fitting a linear regression using the weather indicator variable, for example, which would be x in this case. And by learning linear regression, we can see how much this variable explains or predicts our feature of interest. In this context, one can actually show mathematically that the Pearson's correlation, for example, is the standardized slope of the linear equation. So in other words, basically, the stronger the correlation between the target and the variable that we are looking at, the higher the predictive power of this variable, right? So the bottom line here is, by finding correlated data in large data sets collections, we are able to explain or to predict other variables of interest. In this talk, I'll be talking a lot about Pearson's correlation, but as will be clear later, our techniques and methods, they actually also work with any other correlation. One could use, for example, Spearman's or mutual information for finding nonlinear correlations. So let's formalize this query more formally. So we start with a query table, right? And we assume that this table has a join column and one target column, Q. And the goal is to find the top K tables in a table collection such that the candidate table not only is joinable on the join key specified, but it also has to contain a new column C, which has a strong correlation with the target column Q, right? And let's take a closer look at this example. So the key operation here is essentially what we call a join correlation, right? We have two tables in the left, and we want to perform a join between these two tables, which will generate the table in the right, according to this join key. We may need to apply some aggregation functions when we have repeated keys. In this case, applying the mean function. And our goal is to compute the correlation and find correlation between these two variables which are only available after the join. And this is one of the challenges here. How can we actually estimate this correlation without having to materialize this join, which could be very expensive in large dataset collections, and especially when tables are very large, right? Yeah, so before diving into our solution for this, let's take a look first at related words. So essentially, the problem of finding correlated columns in a single table, if you have only one single table, the rows are already aligned. So you could speed up this process just by doing some vector normalization and using existing algorithms for vector similarity search that use the cosine distance, for example. However, this is not applicable to our scenario where tables are not joined and therefore the rows are not aligned. There are also some recent work on finding joinable tables in data lakes and large data repositories. And most of these problems, they work with this idea of Jacquard containment, which is essentially measuring the ratio of the overlap between the keys in the joint columns divided by the number of keys in the query table. So essentially, this is a percentage of keys that join in our two tables, right? And this, of course, is an expensive problem, and there have been many algorithms that propose to solve this problem. This is essentially a set overlap. It's a set overlap search, and there are versions of there are algorithms that solve this problem exactly. So, for example, we have many prefix filtering algorithms, and recently, Josie is one algorithm that has been proposed for this setting where we have large tables. We have also some approximate solutions for this search. For example, LSH ensemble, Lazo, NGB, KMV are all approaches that try to approximate the results. They basically they achieve efficiency by approximating the results at the expense of some approximation error. So in our approach, of course, those solutions, they don't necessarily solve our problem. They are halfway there, but not there, right? So in our approach, we take a seamless approach, right? We essentially we propose an approximate solution as well that trades off accuracy by performance, and we split this problem into steps. The first one is finding the top k most joinable tables. And for this, we could, for example, use one of those solutions I just mentioned. And the second step is re-ranking the candidates using the correlation estimates that in our solution, we compute using data sketches. So essentially, we are not materializing the joins, but first we compute data summaries of the data sets of the tables, and then use these data summaries to estimate efficiently the correlations. So here is an illustration of how this happens. The idea is that we have initially the tables. For each table, independently, we create sketches for each of these tables. And using these sketches, we create an inverted index that supports queries. And then when the user provides a query table, we compute the sketch for this new query table, and we process a query using the index that will retrieve the top k most joinable tables, right? And the last step, finally, is once you get the most joinable tables, then you estimate the correlation between these two tables using data sketches, and you re-rank them using the correlation estimate. At the core of our approach is essentially this idea of correlation sketches, which are essentially an extension of KMV sketches, which allows us to perform this estimation efficiently without having to materialize the joins. So the key idea here is that we use hashing functions to create a randomized sketch of the data, And this sketch allows us to recover a uniform random sample of the join table without actually having to materialize a full join. Once we recover this random sample, we can apply any correlation estimation. Could be Pearson's, could be Spearman's, or any other correlation estimator between these tables. And again, it allows us to build these sketches, allows us to build these indexes and to perform this estimation at query time. So let's take a closer look at how we compute these sketches. Essentially, we use one hash function, and we apply this hash function for each key of the join key on our table, which generates this table on the right. And then we only keep in the sketch the rows that contains the minimum values of this hashing function. So essentially, we map the join keys to a number between 0 and 1, and we only keep k smallest samples that in our hash domain, right? In the final sketch, we only need to keep the hashed keys, which is called on the left, and the numeric value associated with each key. So to find joinable tables using this sketch is essentially a set overlap operation, right? If we find the sketches that have the highest overlap between the hashes, then we are approximately finding tables that have a high joinability score, that have a high Jacquard containment. And on the other hand, we can also use these sketches to create a join sketch table, which will allow us to estimate the correlation. Right. In this case here, we have 2 columns of the joinable sketch, which is effectively a uniform random sample of the join table, of the full join table. Now, another advantage of these sketches is that not only it allows us estimating correlations, like we just shown, but it's also a KMV sketch. What this means, basically, we can estimate other statistics. For example, we can estimate the Jacquard containment or Jacquard similarity between the 2 tables, between the join keys, and we can estimate the full join size. So in summary, it actually gives us lots of different statistics about the tables that we are retrieving. We evaluated this experimentally. And in this plot here, we show essentially the accuracy of the estimation. In the x-axis, we have the actual Pearson's correlation. In the y-axis, we have the correlation estimated by the sketch, right? And this is bivariate normal distribution, synthetic data, and we see that all the estimates are close to the diagonal, which is the ideal values that we would like to see here. We also applied this to real-world data, and these are very large data set collections from 2 different data catalogs. But here we can see that in real data that do not follow a normal distribution, we have a much higher variance. For example, you can see overestimates here on the World Bank Finance and in the New York City Open Data. However, in the paper, we do a theoretical analysis, and we actually show that it's possible to detect when such errors exist, when they will happen, right? So in this figure here, we can see that just by filtering out joint sketches that have a small sample size, we can achieve we can detect that the estimates are not accurate. In the paper, we provide some confidence intervals based on Hofstadter bounds that gives us an idea on how much accurate are the estimates. And we show that they not only depend on the sketch size, or actually in the intersection of the sketches, but it also depends on the range of the variables that we are looking at. So Of course, if we use only these estimates for ranking the tables, we will have lots of false positives in the top. We have inaccuracies. So we also we derived this framework, which is a very simple framework, which instead of maximizing only instead of putting in the top of the ranking only the sketches that have the maximum as correlation estimate, we apply a penalization factor based on the risk that these estimates are incorrect. So you can see here that in the left we have the correlation estimate produced by the sketches, but we multiply that by a risk factor, which can be seen essentially as the probability that the estimate is wrong, right? And we can actually use many approaches to compute this error. For example, we could use Fisher Z transformation, and this assumes that the data is normal. It follows a bivariate normal distribution. We could also use bootstrapping-based confidence intervals, which is expensive to compute. And we also propose this new approach using a Hopf-based bound, which I just talked about, which is actually does not assume any data distribution and can be computed at constant time. So it's more efficient than doing bootstrapping-based methods. So we evaluated this approach experimentally as well. So basically compare all of these, the accuracy of the ranking, and also compared with applying these bounds, right? Different ways of comparing these bounds. We use as baselines simple Jacquard containment, which is what you would get if you just find joinable tables, and also with a random baseline. So here we have some results, and this shows that essentially our approach, which takes into account the Pearson's correlation plus times the Hopf bounds, the interval of the width of the confidence interval, is much better results than just using Jacquard containment, for example, and also using just the simple Pearson correlation. And well, in the left here we are comparing accuracy when the correlation is above 75, which is essentially strong correlations, and in the right we have moderate correlations, right? And depending on these settings, we see that the approaches, they have different performances, but exceptionally in the case where we want strong correlations, our Hopf bounds are better, but in any case, using the bounds help in some way. We also compare the efficiency of this approach, right? If we given two pairs of sketches, how long does it take to estimate the correlation compared to materializing the full join between the two tables and estimating the correlation? So in this table, we break down the time it takes to do this computation on the full data. Here in the left side of the table, we have, for example, that computing the full join may take on average 42 seconds. When to do this with a sketch, the join of the sketch takes only a fraction of a second, only a few milliseconds, right? So this represents essentially a 3-order magnitude improvement compared to the baseline approach. And we also evaluated the time it takes to do this end-to-end instead of just computing the correlation estimate. So if we use an index, we issue a query, retrieve top K most joinable tables, and then re-rank using correlation estimates. We see the most queries, they are answered in less than 200 milliseconds, which is fast enough to use this in a data search engine-like setting where we want interactive response times. So in summary, we propose this approach to compute correlation estimates using data sketches. And the main advantage of this approach is efficiency, right? However, it still has some limitations. We The main limitation here is, for example, we don't take into account the level of joinability when we are re-ranking the tables in the second step. What do I mean by this is essentially this. When we join two tables, and here we are seeing another example, we have two tables in the left, which generates the join table in the right. Sometimes the join keys in the left, they are not present in the candidate table. And this means that when we do a left join, we will have a table with missing data. So we can quantify the amount of missing data. Essentially, if we compute the Jacquard containment, it will give us a way to measure the level of joinability between these tables. And our previous approach doesn't take this into account, right? In the worst case scenario, we can have tables that have only two rows, lots of missing data, but only two rows, and still have a perfect correlation, which is a problem for, obviously, for many applications, right? And here's another issue. So it does not take user preferences into account. So for example, here, each row here represents one table. In the left, we have the level of joinability. In the right, we have the correlation of the same table. And which one is better in this case? Is it better to have a table with perfect joinability but correlation 0.7, or is it better to have a joinability of 0.9 and perfect correlation, right? So, and another issue is that in practice, if there are too many joinable tables, we may need to only retrieve the top, let's say, top n joinable tables, and then estimate correlations on the top n candidates, right? And this actually may lead us to miss some strongly correlated tables that have only a slightly worse joinability, right? In this case here, you can see that there is one table that has 0.9 joinability level score, but it has perfect correlation. And it probably is better than the 5th of the 6th ranked position in this list. So in this paper at ICDE 2022, we essentially we propose this revision of this problem definition, which essentially replaces the second step. Instead of optimizing for ranking, finding tables that have the highest correlation, we want to find tables that optimizes weighting function, which combines joinability and correlation. And obviously, there are many function choices of how to combine these two measures. But if you take the weighted geometric mean, for example, we have this function. And if we assign, in the paper, we consider these two special cases, essentially. One case where you are only interested in high correlation. So the weight for correlation is 1 and the weight for joinability is 0. And this resolves to the same case as the SIGMOD paper. And we are also looking at this equal weights setting where both are desirable, right? And this resolves to this weight where it's essentially a product between the joinability and the correlation. So in this paper, we also propose a new approach for the problem. It's again based on sketching algorithms plus inverted indexes. But the main difference here is that now, instead of doing this two-step approach, we derive this new hashing scheme, which allows us to basically reduce the problem of finding correlated tables to this set overlap search problem. Essentially, instead of doing two steps, in one single step, we can find tables that are both joinable and correlated by just doing set overlap search, right? And we again use an indexing approach where we use fast top K processing algorithms to retrieve tables that have that maximize this overlap between the sets. So here's how it works. Essentially, we build on our previous work. We take as input the full table, then we compute the correlation sketch, And then in the last step, we transform the rows in this sketch in a set of terms, which essentially combine information of the sketch. So each term here is holding information not only about the join key, but also about the numeric value in the other column, right? More formally, this is what we do. We, again, we take as input the hashed keys, age of key, and the numeric values C sub key, K. And our terms are essentially another hashing layer, where we take as input the hash of the join key, age of K, concatenated with an IG +1 or -1. And this +1 or -1 depends on the average of all the numeric values. So let me actually take a step back and show you the intuition for how this works. So essentially, this is based on this idea of quadrant-count ratio correlation, which is a similar correlation measure. So it's similar to Pearson's, but it's also in the range -1 and 1. It's close to 0 for uncorrelated data, and +1, -1 for strongly correlated data. However, it has a very simple formula. So for example, it simply counts the number of points in each quadrant. So in this example on the right, we are counting the number of points in the first quadrant and in the third quadrant. And we subtract the points in the second and fourth quadrants. In this case, we have 6 - 2 divided by 8 is equal to 0.5, right? So why do we do this, right? The key idea here is that we do not necessarily need to estimate the correlation for every single table in single joinable table in the database. We only need to find the table to have the maximum overlap. In this case here, for example, we have, if you want to find strongly correlated tables with positive correlation, we just need to maximize the ratio of points in the first and third quadrant. And if you want to maximize strongly negative correlations, we only need to maximize points in the second and fourth quadrants. And of course, if you want both positive and negative, we simply take the maximum between these two measures. So essentially, in our hashing scheme, this is what's happening. We have 2 columns, and this is a representation of the tables in the real line. So the labels here mean the join keys, and each point is a join key, but they are placed according to the numeric value in the table, right? In the target column, C and Q. The first step, as I said, is to subtract the mean. So essentially, you are mean centering the data, so they are comparable. After this mean centering, we essentially can see here that tables, the points that do not join, we can divide this in 3 cases. Points that do not join, for example, here the yellow points, J and H, they do not join because the join keys are not present in both columns. So J is not present in the other table, so they do not match. For points that are present in both tables, for example, in this case, we have, for example, B, A, and C. B, A, and C, they are present in both tables, and they are above the mean. They are to the right of 0 here. So they both match, and they are in the same quadrants if you look at the previous picture. So essentially, this hashing scheme is matching these points. The set of terms will only have high overlap if they are both joinable, and if they are in the same quadrants in our scheme, in this scheme of the QCR correlation. So in summary, For each table in the collection, we first compute the correlation sketch, build the indexing terms, and then we add those sketches to the index using these hash terms. And then we use standard query processing to find the sketch that maximizes this score. S plus for strongly positive correlations, S minus for negative correlations. And in the paper, we have also some theoretical analysis that shows that this score is actually a good approximation of the QCR correlation that we are trying to optimize. So again, we did some experimental evaluation. We use again synthetic data sets and New York City open data. And here we evaluated actually two methods. The first one is the QCR overlap. It's what I just described. It's just set overlap search between the hash terms using the QCR scheme. But we actually can also combine this with the SIGMOD approach, where we first find the tables using the QCR scheme, and then we re-rank the tables using an actual correlation estimate. So this is what we are calling here QCR correlation. And we use as baselines the previous approach, where we simply find the overlap using the hashed keys, and the proposed approach in the SIGMOD paper, which is set overlap over the hashed keys plus estimating correlation with the sketches. So here are the results, and we essentially show that using QCR scheme, it actually helps. It's always better than using the previous approach. So if you use QCR overlap, or if you use overlap plus correlation, you always have an improved score. And essentially, the correlation estimate, it can improve in the top K, especially in the top 5 positions. And here, again, sorry, we are looking at the weight combination of high correlation and zero joinability, which is the same objective from the SIGMOD paper, right? And this is for the New York City collection. For synthetic data, we have similar results. Again, we have best results with both overlap and QCR plus overlap and QCR plus correlation. If you look at the balanced setting where we want both correlation and joinability, we again attain best results here. And we actually see also that in some cases, we even have very comparable or even better accuracy if you just use the QCR overlap. The QCR overlap is optimizing for this product of joinability and correlation. So sometimes it can be even better than estimating the correlation and re-ranking based on the correlation. So here, for example, shows this just to illustrate another point, which is QCR usually attains a better recall over the previous approach. The reason why it's better here is essentially it's able to retrieve more tables than it makes more tables available that have high correlation and joinability compared to the baseline. So here's more or less the same data. We are just ranking the results based on accuracy. Here we have multiple settings here, not only of QCR index versus CSK index, but we also have different parameters such as the number of top K return results and also the sketching size. And for any of these configurations, we see that QCR is always better than the baseline from the previous paper. And another interesting thing here is if you compare the best approach using the largest sketch size, in this case 1024, even in this case, the QCR approach attains better results with a smaller query time. The query, that column in the right here, for example, you can see that the previous approach takes 17 milliseconds, where the QCR approach takes only 13 milliseconds. Yeah. And just another view of the same data here, we are plotting them in 2 dimensions. Here we have speed versus the accuracy metric. Basically, we are measuring both recall and precision of the ranking. We want things to be in the top left, which is where we have the maximum accuracy and the maximum speed. And we see here that each point here, each shape, the size of the shape here is essentially the number of entries in the sketch. So larger entries here, they mean takes more storage size, and it also takes more time because of that. And in any case, any combination of cases here, we can say that here in the top, the QCR approach is typically faster for the same level of accuracy. It's always is able to achieve a better accuracy compared to the baseline. So in conclusion, we have defined this problem of joint correlation queries, and we described 2 different methods for indexing and querying large collections. And there are plenty of future work that we can improve here, right? So right now we are actually exploring other measure of correlations. So for example, we want to look at correlations that not only support numerical data, but also that support categorical data. As in real world, many data sets contain categorical variables. Right now we are exploring with using mutual information. And we already have results showing that it's also possible to estimate mutual information for both numerical and correlated, both numerical and categorical variables. And there are also multiple extensions. For example, if the columns are text data, what does it even mean to compute correlation? Maybe we need to apply some embedding approach to convert the text variables to numbers and then compute correlation. Or maybe there is some other approach that makes more sense, right? And there's also other types of joins. So for example, we are considering only equijoins. We only look at joins where the keys are equal. So what if we want to do spatial joins where we want to join rows where the distance of one point is smaller than a given threshold? This is a different type of join that's typically used in other settings that could benefit from this type of approaches. How can we actually compute sketches that can solve this problem, right? And there's all sorts of combinations. What if you want to do spatial queries with textual data or audio or video and so on, right? Yeah, so with that, I'd like to thank my co-authors, Aline Bessa, Fernando Chirigati, Professor Christopher Musco, and Professor Juliana Freire, and for the funding that we received for doing this work from the ARPA, NSF, and a Google Research Fellowship. Thanks. I hope we have some time for questions, if anyone has some.
All right, awesome. Let's thank the speaker.